Okay,
Great.
so next we have Lara from Virginia Tech, and will be telling us something about elliptic Calabi-Yau geometries and sort of how they appear in F-theory. So take it away, Lara. Thank you.
Thank you very much. And thanks to the organizers for a very good, very eclectic meeting. I have enjoyed all the different ideas that I've gotten to hear the last 2 weeks. So thank you very much. I have to apologize for joining you from my professional basement here. This is the only toddler-proof room in my house at the moment, so that's why I'm hiding in the basement. I'm going to be talking today about primarily work that is in progress with James Gray, also at Virginia Tech, and Paul Ullman, who is at Uppsala. It's a paper that we've been working on for quite some time and hopefully will appear very soon. I'll also refer to some older work with various collaborators as well. So let's begin with a little bit of motivation. So the goal of today's talk is more broadly a better understanding of possible string effective theories. So as we've seen in many different aspects of talks through the last 2 weeks, those that involve string compactifications, the question of string geometry is intrinsically linked to which field theories you can have in various dimensions. So from an ordinary field theory perspective, you're free to write down whichever consistent field theory you choose. From a string compactification point of view, that choice is entirely or nearly entirely determined by the choice of a background geometry, which is highly restrictive for in terms of what field theories you can produce. So the question of which geometries are actually of interest and allowed in realistic string compactifications in various dimensions is an ongoing and open one. We know that quite a lot of these geometries are very difficult to construct in general, or not necessarily complex or Kähler geometries. But we also have many open questions, even in the simplest class of these, which are Calabi-Yau manifolds, which have made appearances in many talks in the past 2 weeks. So even for the simplest class of compactification manifolds, we don't know whether the set of Calabi-Yau 3-folds and then 4-folds, for example, are finite. And a weaker question that appeared in Waddy Taylor's talk yesterday is the question of topology, i.e. do we know if the defining topological invariants of Calabi-Yau 3-folds are in fact bounded numbers. So in this talk, I'm going to take a sort of step in towards that direction by considering Calabi-Yau fibrations in various contexts. And I'm going to be particularly looking at F-theory compactifications as sort of a playground for exploring some of the effective physics and geometry of Calabi-Yau 3-folds. So in the structure, the question of fibrations is probably familiar to most people, but a quick reminder for a general audience. A fibration is simply a surjective morphism between 2 spaces, X and B. We refer to X as the total space or complete space of the fibration, and B as the base, such that for almost all points, the fibers are homotopic, i.e. the inverse image of a projection is the same. And if we have a continuous map that goes from the base back up to the total fibration, obeying this property, then this is what's referred to as a section to the fibration. Okay. So why consider Calabi-Yau fibrations? This appeared in both James and Waddy's talk yesterday, so I apologize for a little bit of repetition from those two, but hopefully I'm going to hit slightly different points than happened yesterday. So for starters, from a field theory point of view, we understand that fibrations play a role in many different string dualities. For example, F-theory, M-theory requires the existence of elliptic fibrations. Heterotic F-theory duality involves elliptic and K3 fibrations, heterotic type 2A, and so on. In addition, being able to describe a given geometry as a fibration significantly simplifies the geometric description in that you can sort of build the pieces of a fiber and a base independently, and this increases calculability. It allows you to infer information about the topological invariants that I just referred to. For example, intersection numbers, it constrains the form of the metric. So it enters into many possible questions that one would like to address geometrically. And as was mentioned yesterday, another major reason for considering fibrations in the context of Calabi-Yau geometries is that they give you what, in my opinion, is probably the most promising window into proving finiteness of this data set. So it has been proven for quite some time now, thanks to Gross and Grassi, that elliptically fibered manifolds are finite for Calabi-Yau 3-folds, the set of genus 1 fibered. I'll make that terminology more precise in just a second. The set of genus 1 fibered Calabi-Yau 3-folds is finite. And the motivation for this study, as actually mentioned in these papers, particularly in the work of Mark Gross, is the hope that this the insight into why this is happening could provide insight into finiteness for all Calabi-Yau threefolds. More recently, this result has been extended to Calabi-Yau fourfolds by Dicerbo and Spaldi in 2016. They've proven in particular that there's a finite number of bases for elliptically fibered 4 and 5 folds. Okay, so maybe it'll help you understand something about the data set of all Calabi-Yaus, and it's useful for string dualities and effective field theories. Terminology, I've interchangeably in various places in the last 2 slides referred to elliptically fibered or genus 1 fibered geometries. Let me try and be a bit more precise about that. So the inverse image of points on the base in the case of an elliptic or genus 1 fibration is in all cases a T2, a Calabi-Yau 1-fold. However, if a section exists, then we can introduce an addition law on each of these fibers, and we refer to that as an elliptic fibration, i.e. as a complex manifold, the fiber is an elliptic curve. So if no section exists, it is still torus or genus 1 fibered, but if it emits a section, then it's elliptic. Let's pictorially understand that for a second. So if here's the base, here's our projection map. Over each point in the base is topologically a T2, which is shown by these curves here. This may be degenerate over non-generic points in the base, reducible curve in this point. And if you have a section that hits each fiber exactly once, this is what's providing your addition law on the elliptic curve. If you do not have a section, then there will still be so-called horizontal divisors, i.e. things that cut the fiber. They're just going to be end-sheeted covers of the base. We refer to those as multi-sections. Okay, so a few results that are important in the discussion of Calabi-Yau fibrations. First is that the very notion of whether or not you have a fibration for Calabi-Yau n-folds where n is greater than 2 is a deformation invariant statement. So this is actually meaningful from sort of the topological classification of the manifold. In addition, Calabi-Yau n-folds can actually only be fibered by m-folds, i.e. subgeometries with C1 equals 0, where n is less than the dimension of the space. So for example, 3-folds can admit elliptic and K3 fibers, 4-folds can admit elliptic K3 and Calabi-Yau 3-fold fibers, and so on. As I mentioned, n greater than 2 is important here. K3, of course, you can move in the moduli space of K3 and create or destroy fibrations. For 3-folds and higher, that cannot happen. Okay, motivation, I mentioned this previously, behind Gross's theorem is that maybe understanding that elliptically fibered manifolds are finite can tell you something about all possible Calabi-Yaus. So what is the idea behind that? The short idea is Reed's fantasy, namely that we understand that basically all Calabi-Yau 3-folds that we know how to make can be connected to one another via so-called geometric transitions, i.e. flops and conifolds. So if you can build a finite data set, in this case, elliptically fibered geometries or genus 1 fibered geometries, and you can transition them via controllable flops and conifolds into other manifolds in which you destroy the fibration, if you can understand the ways that fibrations can be created or destroyed, then in principle, you have sort of a modular way of attempting to prove finiteness of all Calabi-Yaus. This has not been done yet, but that's sort of the intuitive motivation. So yeah, can these geometric transitions be characterized or classified? For example, it is known that for the data set of complete intersection Calabi-Yau 3-folds in products of projective spaces, all of them are linked by conifolds. So this is one set where you can watch those fibers appear and disappear very explicitly. Okay, a few observations. It is possible to systematically construct very large data sets of Calabi-Yau fibrations. This has been done again in this sort of modular way, which makes this easier, is that you can create bases. The first data set of these were 2D toric bases put together by Morrison and Taylor, and then you can tack elliptic fibers over the top of that. Wadi and I extended this to Calabi-Yau 4-folds for classes of simple rationally fibered toric bases. You can study fibrations in a lot of different contexts, which various authors have done, and you can build up big data sets of fibered Calabi-Yau geometry. You can also ask the inverse question, which is, if you hand me a random Calabi-Yau out of some data set, how special is it to admit a fibration? And I think for quite a while in the sort of string compactification literature, it was understood that you had this extra properties like string dualities when your geometries were fibered, but this was assumed to be sort of a non-generic structure, a special case where two different types of compactification might meet. What we're seeing now, and this was alluded to in both James and Wadi's talk yesterday, is that that is not actually the correct viewpoint. It seems that, in fact, basically, if you throw a dart at a data set of Calabi-Yaus, you're going to hit something that's elliptically fibered. So this is a bit of a repeat from yesterday, but bear with me for a second. If you consider your favorite data set of Calabi-Yau threefolds, say, Weierstrass database or continuous section Calabi-Yaus, the immediate observation you can make is that almost all Calabi-Yau threefolds and fourfolds are fibered with every possible dimensionality of fiber that they can admit. So if you throw a dart at a fourfold, it's not just elliptically fibered, it's K3 fibered, it's Calabi-Yau threefold fibered, and so on. The immediate observation number 2 is that when you look at one of these manifolds, in general, it does not just admit one fibration, but the same manifold can actually be described many different ways, order tens, hundreds, or even thousands of different ways as a fibration. So you can pull the manifold apart, kind of, Lego style, into different decompositions as a fiber and a base. And the same geometry can have many different decompositions, all of which can teach you interesting things about the structure of that geometry and the field theories that will live over it. So the genericity of fibrations, here is the famous Hodge number plot from the Weierstrass database. This is an image that is quite old now, and this is much denser, and this was mentioned in Wadi's talk yesterday. The blue dots here are the Hodge numbers that are known to correspond to elliptically fibered manifolds, and thanks to the work that Wadi and his students have done, this is now much denser. And as he mentioned yesterday, about 99% of the manifolds in Weierstrass are understood to be elliptically fibered. Other studies in toric datasets included the work mentioned here by various people over the last 20 years. For Calabi-Yau threefolds, the set of complete intersections, so this is looking at higher codimensional descriptions of manifolds in simple products of projective spaces, my collaborators and I attacked over the last couple. And there you can search for sort of two things. You can look for so-called obvious fibrations, and these were the ones that Wadi was mentioning yesterday, also James alluded to in his talk. These are Calabi-Yau fibrations that are manifest from the algebraic description of the manifold in the given ambient space. So here I've highlighted the famous CYn manifold with Hodge numbers 1919. If you look at the description of this guy, this has the two columns of this matrix denote the multi-degree of two defining equations in a product of P2, P1, P2. What does this mean? Well, the first equation, A013, simply defines a rational elliptic surface in P1, P2. So this is defining the base, and then putting the solution to this first equation into the second, over every point in that dP9, or rational elliptic surface, you end up with a cubic in P2, which is a genus 1 curve. So this manifestly is a fibered manifold, genus 1 fibered. You can play this game with other data sets, and this was done by Gray, Haupt, and Lucas for the data set of CC fourfolds. And you can track both the obvious and, as I'll talk about in a moment, the non-obvious elliptic fibrations. So here, within playing the same game of sort of plugging in equations and looking at their solutions, this is a elliptic Calabi-Yau fourfold, and I've highlighted in different colors here, the blue, red, and green. These are the largest one here. So green and up is a description of a Calabi-Yau threefold fiber over every point in a P1 base. That's the last entry here. The red and up is a K3 fibration, and the blue degrees are the description of an elliptic fibration. So this is a fourfold that is Calabi-Yau threefold, K3, and elliptically fibered, manifestly from its algebraic form. So various scans were done to count how many such obvious fibrations. You heard a bit about those yesterday. Something that you did not hear so much about is that when these fibrations do have such, when these manifolds have such descriptions of fibration, there can be many. So those can be obvious. Whoops. So here I've taken the same configuration matrix, which again is just denoting the multi-degree of some defining equations in a simple product of projective spaces. And it is clear that row column permutations of this are not changing what you actually mean by the Calabi-Yau. So simply by rearranging rows and columns, you can view the same manifold as an elliptic fibration or genus 1 fibration. Over writing it this way, this blue highlighted stuff is the description of a genus 1 curve over P1 times P1. And rearranging it, we can actually change this to the description of an elliptic fiber over dP1. So there can be more than one obvious fibration for a given algebraic description. Those can be counted, and as you can see, the number of fibrations per configuration, this top plot is for fourfolds, the bottom one for threefolds. There can be as many as 350 different descriptions as a fibration for one Calabi-Yau fourfold. Okay, so a few other comments on this. And again, why are we sort of interested in this general structure? Remember, the goal here is to try and extract structure that is going to be of use in saying something both about field theory and about what Calabi-Yaus are possible. So with my collaborators and I a number of years ago, we scanned for obvious fibrations in the Calabi-Yau threefold data set, and we found hundreds of thousands of them. However, there's no guarantee that that was all of them. So we devised algorithms to actually exhaustively search for all of them using criteria due to Aguiso and Wilson. And what we find is that, as mentioned before, 99.4% of all Calabi-Yau threefolds are manifestly genus 1 fibered. And in fact, this multiplicity of fibrations, we find that this can be very large indeed, even within the set of Calabi-Yau threefolds, once you relax the obvious fibrations and are just searching for any possible fibration. So for one geometry that was written as an anti-canonical hypersurface in dp7 times dp7, we find 15,000 inequivalent fibrations for that geometry. For one manifold, and it is unique in the set of CC threefolds, the shown manifold that I highlighted earlier, there is actually an infinite set of elliptic fibrations that are possible. And this was actually known to some extent before by Aguiso, Asmawal, and Gross. I should mention that I'm not highlighting it here. I'm just writing simple algebraic descriptions in products of projective spaces or toric hypersurfaces. However, these results in the genericity of fibrations also extend to Calabi-Yaus that are non-simply connected, i.e. those that are constructed as quotients, GCC constructions, and others. Okay, so all of that is a bit of backstory to say that contrary to at least my belief a few years ago before we started looking at this, is that generically Calabi-Yaus seem to be very fibered indeed. So if you can understand fibrations, then again, you have a chance of understanding something quite general about string compactifications. So for today's talk, I want to try and unpack a little bit of that, and I want to understand some features of this fiber-based decomposition. So the ways that you can pull apart a manifold into its fiber and base. The genericity statements that I've referred to in the last few slides all apply to genus 1 fibered 3 and 4 folds. That is, I have not explicitly been sort of searching for just geometries with section in what I was writing there. I was simply looking for the existence of a fibration. This is in contrast from a string dimensional reduction point of view to what is normally assumed in the context of F theory. So in the interest in F theory in the last decade or so, there has been a strong focus on geometries that have not only admit a section, but take a very specific form with respect to that section, so-called Weierstrass models, in which the entire geometry, its fiber exists as a very particular description of an elliptic curve. This equation here, I'm going to define this a bit more precisely in the next slide. So the important questions that I want to look at from the point of view of F theory and also thinking more broadly about characterizing and classifying Calabi-Yau threefolds is, how can I sort of understand from this tinker toy, take the geometry apart point of view, how different an elliptic fibration is to a genus 1 fibered over perhaps the same base? That's going to be a question. And this is something that a lot of progress has been made in the last 5-6 years, but I'm going to highlight some important questions that are still open in this context. So first, let me specify why we're interested in so-called Weierstrass models, particularly for F theory. So Nakayama's theorem says that any geometry, Calabi-Yau fibered geometry with section in the elliptically fibered manifold is in fact birational to a so-called Weierstrass model. The description of these are based on the work of Deligne for elliptic curves and generalized by Nakayama to elliptic fibrations. And schematically, the idea is that you can define an elliptic fibration via a cubic constraint within a manifold described as the projectivization of 3 line bundles of said form. The Calabi-Yau condition enforces that the line bundles, one of these, the O to the 3 here should be L to the 3. Here L is the anti-canonical class of the base, and this provides for you a C1=0 manifold. The reason that this is nice is that each of these coordinates in this description can be mapped into, in any elliptically fibered geometry with section, can be mapped one-to-one. This coordinate Z can be identified with a unique 0 section of a holomorphic section, and so on. The coordinates X and Y in this projective bundle can be mapped explicitly into sections that exist in your geometry. From a sort of more birational geometry point of view, the idea is to blow down components of reducible elliptic fibers. This leads to the Kodaira-Tate classification, which do not intersect the zero section. And the physicist version is this projective bundle. You can do a variable change to describe the fiber as a degree 6 hypersurface in P1, 2, 3. So I'm not doing justice to this construction, but the point I wanted to make here is that if you hand me any, however it's described, torically, non-torically, Sophian construction, anything you like, if you have a geometry that is fibered and you have the section, then you can map it in an explicit way into a Weierstrass model. Okay, in F-theory, Weierstrass models play a really particular role. So let me say very briefly for the non-experts in the room, what is F-theory as a string compactification and why are we interested? F-theory is the geometrization of type 2b string theory with mutually non-local 7 branes. The idea is that an elliptic threefold, described as some fiber over a base B, encodes information about type 2b compactified, type 2b string theory compactified over the base B. The axiodilaton in type 2b has an SL2C symmetry, and we're going to interpret that as the symmetry of a 2 torus. If you fiber a 2 torus over every point in B, this actually encodes information about the axiodilaton at each point in the base. And you can argue very nicely, as Baffa did many years ago, that T2 degeneration should correspond exactly to the location of 7 branes within a type 2b description. The singularities of elliptic fibers have been classified. I could have mentioned one on the base by Kodaira and Tate. And so what you can use is using an elliptically fibered geometry as a trick or a tool to encode information about type 2b physics in a not necessarily weakly coupled perturbative way. The field theory is encoded in geometry and algebraic geometry in particular. In this context, Weierstrass models are natural. Why is that? Because the Weierstrass description gives you a very minimal, simple description of the fiber for which over each point in the base, you have a well-defined value of the axiodilaton that you can map to over it. So it is a minimal and sort of well-understood description. There's a nice limit between F theory and type 2b, a nice limit that you can take in this context, which is well understood. So the geometric ingredients, an elliptically fibered Calabi-Yau threefold. This is something here, obviously we do threefolds or fourfolds. If we're doing physics in 60 or 40, I'm going to focus on 6 dimensions for a minute. So elliptically fibered threefolds in this context, using the tools we described previously, we can have a map into Weierstrass form. This will give us a simple description of the elliptic curve in this way. And degenerations of this elliptic fiber are going to encode the position of 7 branes, as we described. For such a simple fiber, the discriminant locus is a divisor in the base, which is easy to write down. These 7 branes will carry non-abelian gauge groups over them, and which non-abelian gauge groups you can have from a stack of 7 branes will be understood via what the degenerations of the elliptic fiber are. So divisors in general correspond to gut symmetries, and which gut symmetries are given by the affine Dingman diagrams that can be found in the reducible fibers under resolution. So if you resolve the singular fibers, for example, here is the Dingman diagram of B7 over a point in the base for which the 7 brane is degenerating, there exists a resolution which from sort of an M theory point of view would lead to a resolved B7. Intersections of 7 branes correspond to matter, and in 4 dimensions, of course, we can also have Yukawa interactions. Okay, F theory is also, in addition to being thought of as a limit of type 2b, it is also very helpful to be able to think of F theory as a limit of M theory. So the idea, very roughly, is that M theory on a given manifold Xn can be understood as F theory on the same manifold across an S1, i.e. M theory on a resolved elliptically fibered Calabi-Yau Xn can describe the Coulomb branch of a theory, M theory, and in the singular limit for which the fiber goes to 0 volume, you can uplift in 1 dimension higher and understand this as a limit of M theory, which we are going to use to define F theory. In 6 dimensions, the sort of multiplicity of the M theory solution, the number of states, number of tensor vector and hypermultiplets that can be written down. It's very easy to do this field theory to geometry mapping. Anomaly cancellation has a simple form in 6 dimensions. And your degrees of freedom are very nicely parsed for you for Calabi-Yau threefolds via a geometric theorem due to Shioda, Tate, and Lazier, which says if X3 is elliptically fibered, then every divisor inside the threefold has to fall into one of 3 categories. Namely, it has to be a pullback from the base, a 0 section, or an element of the so-called Mordauvet group, i.e. the group of rational sections to the fiber. or a blow up in the fiber, a so-called fibril divisor, i.e. the E7 degrees of freedom in my previous slide. Okay, so point here, we have a nice F theory to M theory dictionary that can be useful for us. And we can, in an M theory perspective, we can sort of break up the degrees of freedom in the geometry very nicely according to their role as tensors, vectors, and hypers in the M theory limit. Okay, so now we're going to come to the main thing that I wanted to focus on for the remainder of my talk, which is elliptic versus genus 1 fibrations. So F theory, as it was defined by Vafa and through most of its study in the last 20 years, is naturally defined on Calabi-Yau fibrations with section. Elliptic Calabi-Yau n-folds in Weierstrass form can be straightforwardly classified. They have they're a very simple sort of Lego tinker toy description of a very minimal fiber. There's a single section in this description, as I mentioned, sorry, here. In the Chiodate-Wazir theorem, if you have a Weierstrass model, then it may be singular, but you have no fibril divisors because you're describing your fiber as a single degree 1, 2, 3, 6 hypersurface. You have only a single section, and you have the pullback of divisors from the base. So if you have a smooth Weierstrass model in particular, it's H11 is simply 1 plus H11 of the base. Okay, so it's a simple geometry. It's straightforward to try and build these over various toric base surfaces, and this has motivated a lot of systematic constructions of F theory backgrounds in both 6 and 4 dimensions. But what to do with genus 1 fibered manifolds? There's no systematic constructions. If you drop the existence of a section, you lose this connection to Weierstrass form, and it's a little bit more unclear exactly how many different ways you can tack a topologically T2 fiber over the same base. There are no systematics, and part of the goal today is to try and understand how different genus 1 fibrations can be from their elliptic cousins. These are certainly fine backgrounds to M theory in various dimensions. There's no problem with using them as just straight up Calabi-Yau threefolds. And you expect an M theory, F theory uplift to exist, i.e. there is still a natural limit of the genus 1 fiber that can uplift to F theory in 1 dimension higher. And recent work in the last 6 or so years has shed some light on how to think about that. So the proposal that was started by Morrison and Taylor and also mentioned in a less developed form by Morrison and Vafa is that M theory on a genus 1 fibered manifold should uplift to F theory on its so-called Jacobian fibration. The idea is that any given elliptic curve can have an associated to it a cousin. So this backwards. Any genus 1 fibered manifold has a cousin which admits a section. So how does that work? The Jacobian is a fibration. It's associated to a genus 1 fibration in which you basically perform surgery on the manifold to replace the generic genus 1 fiber with its Jacobian point by point over each point in the base. The Jacobian is defined up to birational equivalence. And for a single elliptic curve, of course, you know that the Jacobian, this is the space of all divisors of the elliptic curve, is diffeomorphic to the elliptic curve itself. For a fibered manifold, this produces birationally equivalent threefolds, and they will have the same J function point by point. And so they're actually encoding, hopefully, the same F theory effective physics. However, the Jacobian will end up having a section. So this has a lot of nice features. So for genus 1 fiber geometries, the Jacobian leads to an elliptic fibration whose fibers share the same tau function. As I mentioned, this allows you to understand what the axiodilaton is doing, what you want. There are techniques to construct a Jacobian algebraically given a particular genus 1 fibered curve. These were particularly done by Arten Tate and Rodriguez-Villegas, and then applied in string theory by Grimm, Brown, and others. For Calabi-Yau elliptic fibrations, as I said before, the Jacobian is birational to a Weierstrass model. For K3 surfaces, they are in fact identical. There is no difference in the structure that can be observed. For genus 1 fibrations, in general, Weierstrass models are not available, and so Jacobian fibrations are the only possibility. The property that these sort of algebraic constructions of a Jacobian fibration admit is that their discriminants must agree. So point by point, the singular locus in the base over which you would have singular fibers must agree for a manifold in its Jacobian. In general, more than one manifold can lead to the same Jacobian fibration. So what this means is that from the point of view of M theory, F theory, you could have a family of M theory geometries in, say, 5 dimensions, all of which could uplift to the same 6-dimensional effective physics. This has been referred to in the group of such manifolds, has been referred to as the Tate-Schaff-Ravitch group in the string literature. More generally, the group of Calabi-Yau torsors is what we're interested in. Okay,
Lara,
so
you have about 10 minutes left.
thank you very much. So in general, elliptic Calabi-Yau threefolds are easier to construct than genus 1. Mentioned this before. Idea is going to be to try and use the Jacobian to characterize X. So I'll highlight the very nice work that happened over the last number of years on this, doing exactly this and uplifting from 5 to 6 dimensions, for example. However, a little bit more broadly, taking this in the context of all the Calabi-Yaus that we would like to understand, more broadly, the set of Calabi-Yau threefolds, this idea is going to have consequences for both physics and geometry, in that if we can understand how similar or different a given genus 1 fibered manifold and its Jacobian can be, that will help us to understand how to systematically construct these and how to bound their topological data. For the case of abelian gauge groups, this has been very well studied. And the thing I'm going to highlight as new material today will be what happens when you have non-abelian gauge groups, i.e. degenerations of your elliptic fiber. So let me provide an example that my collaborator Paul Ullman came up with a couple of years ago that first sort of started us down this rabbit hole of trying to understand these geometries. Here is a particular description of a genus 1 fibered manifold over the base dp1, which you can look at the singular fiber structure of this thing, the number of fibril divisors, and you can see that this looks to be a resolution of something with non-abelian symmetry F4 times U1 in 5D. This is described as a particular resolved quartic hypersurface. Fine. So you have a pretty standard genus 1 geometry that you could use as a 5D background for F theory. The thing that was more novel, at least to us, is that when you write down the Jacobian of this geometry, what you find is a threefold in Weierstrass form with an E7 non-abelian gauge group, as well as discrete gauge groups, terminal singularities, and possibly additional U1s, depending on where you write this down. So this is something where the non-abelian gauge symmetry between the Jacobian, the genus 1 and its Jacobian appear to differ. So let's try and understand a bit more explicitly how this can happen. I should say, by the way, that as you tune this particular model, different things are possible. I won't go into the details of this for time, but you can realize in both the genus 1 fiber for the same general fiber type and its Jacobian, you can realize different possibilities, including where the genus 1 fiber and the Jacobian can agree, where one of them can become a folded version of E7, as I'll talk more about in E7, E6-2, and where you can realize both E6 and F4 as well. Okay, so sorry, just checking one thing here. Yep, okay, I said that. So how is this difference in gauge group actually arising in a genus 1 fibered geometry? What's happening is that homologically reducible components of the fiber are becoming identified. You have what would look like the affine-Dinkin diagram of E7, as you would expect for an E7 gauge theory. However, within homology classes, P1s are becoming identified via the action of a multisection. So a multisection can intersect, say, 2 nodes and homologically put these guys in the same class in a way that you would not expect from a Weierstrass model. So H11 of the resolved geometry in the genus 1 is lower than you would expect for an E7 gauge symmetry. It corresponds to F4. The 2-section monodromy interchanges 2 fibril curves labeled here. And in general, this genus 1 geometry exhibits folded affine-Dinkin diagram structure. So before I say a bit more about where this comes from or where the novelties arise, let me just briefly review the case of a dimensional reduction from 6D to 5D in the case of abelian gauge fields in F theory, and then say why this is going to look different in the present context. So in general, you expect that there are different chains of geometries that can be related to each other with affine groups. As I mentioned this previously, you can start with something that looks like Morris and Park, E7 times U1. And under dimensional reduction, you would expect to get different symmetries, for example, preserving E7, being able to Higgs it, and so on. Let me not get into the details of that just yet, and I'll instead focus on M-theory, F-theory for a second. So M-theory on genus 1 compactifications in 5D corresponds to S1 compactifications of F-theory on elliptic fibers with elliptically fibered manifolds with discrete symmetries. So in particular, if we begin with, for example, 60 F-theory on a Calabi-Yau threefold, which has an abelian gauge group, a U1, this corresponds to 2 rational sections, i.e. Mordell-Weil rank 1, and hence a U1 gauge factor in its gauge group and a field that is charged under that U1. You can consider a dimensional reduction in which you give a vev to a field which has non-trivial winding around the circle direction. So here, y is my circle direction, x is the other coordinates. If I compactify on S1, I can also turn on Wilson line fluxes for this abelian gauge field around the S1 directions. Kinetic mixing between U1KK and U1-6D leads to a multi-section divisor in the 5D geometry. You can break this U1 down to a discrete remnant in 5D. And it is well understood how to drop these abelian gauge fields from the elliptic fiber to the genus 1 fiber and relate the manifold to its Jacobian. The basic properties of this are going to give you not just one manifold, but a family of them. If you have 0 flux along the circle, then M-theory on elliptically fibered Calabi-Yau threefold with torsional cohomology, i.e. terminal singularities, can lead to the same discrete group appearing in 5 dimensions, so U1 times EQ theory. If the flux is non-zero, then you can end up on a genus 1 fibered manifold with multi-section, where it's a Q section where Q is the charge of your field that you started with in 60, and that leads to a single U1. So in general, different possible choices of charged matter and flux along the circle can lead to distinct M-theory vacua in 5D, and hence elliptic genus 1 threefolds with the same F-theory physics. This is where the Tate-Shafarevich group that I mentioned previously enters. These different M-theory vacua all uplift to the same solution of F-theory in 6 dimensions. And so these guys are all forming related physics. And through these dimensional reductions, you understand that relationship. More general possibilities are going to arise, of course, if you have non-abelian gauge fields. And you could imagine fluxes associated to those different factors, more choices for charged matter vacua. So the last thing, and I realize that I'm short on time, so in my last 3 or so minutes, the last thing I want to mention is sort of the physics of these dimensional reductions, which would lead to twisted geometries for which the Jacobian and the elliptic fiber will differ. Where does this come from? So it's also possible to introduce so-called twisted dimensional reductions. These have been studied extensively in pure gauge theory, and I want to just mention in the present context how these can arise. An observation is that you can also, in addition to just writing down fluxes along a circle, dimensional reduction, you can also make choices of discrete twist. So you can twist by outer automorphisms. Here, there is an A mu, which you can map not just to the same gauge field, but to some discrete shift of the gauge field using outer automorphisms. So for example, for E6, you can fold E6 by an outer automorphism to produce F4. This is called folding of Dynkin diagrams. This has led to many novel, interesting EFTs in assorted dimensions. One example is the heterotic CHL string. This is a E8 cross E8 theory in 10 dimensions, which can be folded along an S1 to produce, for example, a single E8 factor. So the picture here is that you want to do the same thing for the dimensional reductions that I'm just describing. You're going to introduce twisted backgrounds, but the key is the symmetry that you're going to fold the Dynkin diagram by, this one here, has to actually be realized in F theory. And so the question is, how is that realized in terms of your elliptic geometry? And how do you see that from an F theory point of view? I'm out of time, so let me skip part of this and just say, here's the punchline. In general, in F theory, you have to be careful about introducing discrete symmetries because from the point of view of swampline conjectures, you believe that all of these symmetries should be gauged. So you are naturally looking for diffeomorphisms of the geometry. How should these guys be realized? To jump to the punchline, we believe that this has already been highlighted in some form in the string literature by work of Grimm, Katfer, and Cleavers, which is that the description of all of this from the point of view of a single elliptic fiber is actually artificial, the Weierstrass model, if you have more than one U1 in play. So there is more than one Weierstrass model that could be written down by choosing which is going to be the 0 section of your elliptic fibration according to this Deligne procedure. This freedom allows you to introduce basically a discrete diffeomorphism into the Calabi-Yau threefold that allows you to attempt to twist the gauge theory by it. So idea is that was highlighted by these authors is that multiple rational sections can lead to addition laws on elliptic fibers. This choice should be something that leaves the gauge theory alone. And they proposed integral large gauge transformations around the circle that could realize this effect. Very similar things are going to allow us to do twisted dimensional reductions with non-abelian gauge groups in M theory, F theory. In our case, we can fold E7 using a discrete automorphism, a Z2, which relates to U1 charge conjugation and interchange of sections. I know that I am out of time, so let me jump to the punchline. I'll skip this. What have I tried to highlight today? I've tried to highlight that Calabi-Yau fibrations form a rich arena for studying Calabi-Yau geometry in general. That if you want to describe the most general genus 1 fiber geometries, you cannot rely solely on elliptic fibrations and Weierstrass models. You have to understand how their Jacobians can be systematically constructed and how different those can be from the genus 1 geometries. To date, not all twisted dimensional reductions of gauge theories can be realized in F theory. There appear to be highly non-trivial constraints that link these two, and that's interesting both from the point of view of physics and geometry. And it appears to play that these U1 gauge group factors actually play a very key role in realizing which symmetries are going to be able to be folded at a non-abelian level. The geometric question is how disparate can elements of the Tate-Shafarevich group be? And we're starting to shed some light on these, as well as introducing some novel folding symmetries into F theory. And with that, I apologize for going over, and I'll stop there.
Great, thanks, Lara. So are there any questions for Lara?
I have a simple question, simple-minded question, Lara. Great talk. About these U1 factors, do they appear in the effective field theory descriptions?
Yes.
At all?
In general, yes, they do. Yep.
And so they are not, you check the anomalies and stuff like that, they're not
Yep.
anomalous. Well, if there is a U1, right, floating around, then I'm always worried about, you know, that that U1 is going to have some some UV divergence. In other words, Landau poles.
Mm-hmm.
So how does one understand that at all?
It's a good question. In general, I think that these types of things are not playing a huge role in what we're looking at in dropping from, say, 6D to 5D. These U1s can go away, right, as you give bevs to things along the circle. From a pheno point of view, obviously, yeah, you know, which U1s you want to keep and which ones you want to get rid of is an intricate question. In general, I would say that.
Yeah, go ahead. I'm sorry.
Yeah, I think what I'm saying is that I don't expect in general for this to play any role in the particular physics that we were looking at, but of course it's a good question for thinking about.
So you're not thinking about something like a dark photon generating a dark photon or something like that?
No, this is, I mean, as the level we're playing this is much more about just geometry and, you know, toy effective field theories in 6D. Of course, if you were playing with these same sorts of things in 4D and for more realistic purposes, then you have to think about a lot of things. All
right, thanks.
Great. So if anyone has any other questions for Lara, maybe they can contact you offline, and we can go to the next talk. So let's all thank Lara for a great talk.